Hello everyone. Today I'm going to introduce our work, Static Detection of Silent Misconfigurations with Deep Interaction Analysis. This is joint work with my advisor Rosita and Anand from Alibaba Group and Ting from UIUC. Nowadays, misconfigurations are everywhere. Large companies such as IBM, Microsoft, Google, and not even mentioned to Facebook all suffered from misconfiguration-related issues, and it caused severe system outrage and huge money loss. And actually, misconfigurations are more common than you think. A large publicly available dataset have shown that misconfigurations are now becoming the major cause of system downtime. For example, it is more than 2 times more frequent than software bugs. It is a surprising result, isn't it? Let me walk you through with a real-world silent misconfiguration example that we collected from Stack Overflow. Suppose you are a Apache user and you want to allow access to only one country, but also to exclude some proxies within that country. This is your intention. And then you may want to write a Apache configuration like that. However, once you plug in this configuration to the system and you start it, and this is the result. Firstly, the specified proxy was actually allowed to access the web server. Note that this is the exact opposite of what you intend to do. And it caused severe security threat. And what makes things worse is that there's no error messages popping out from Apache and making the configuration troubleshooting extremely hard for you. And from that model example, let us come up with an intuitive definition of silent misconfiguration here. So when the users explicitly set a configuration parameter, like deny here, but this setting does not have any effect due to the influence of other related configuration parameters. For example, basically, if you just remove the setting deny in this line here, and the system will behave the same. To understand what is the root cause of the silent misconfigurations, we need to dive into the Apache source code to understand the logic behind it. For example, here, if users set the configuration value of order to deny then allow, and then any IP address that matches with this allow here will overwrite the previous results. So even though users specify that this IP should be blocked, should be denied, well, this result will be finally overwritten by this if it matched with this allow here. So from this example, we come up with an intuition, which is the rules of configurations are actually can be extracted from the source code. And from this intuition, it motivates us to design this paper, ConfigX, this tool, to use static analysis to derive the specifications of configurations. What I want to especially point out is that, so if you only take a look at configurations, it seems you basically don't know what's going on here. It's very hard to figure out what's wrong here if you only take a look at configuration. And if you only take a look at the source code, it seems like nothing wrong here. Or you even think about this code is beautifully written. The only way that you recognize this is a silent misconfiguration, you have to put those two parties together. So this is exactly what we do in this paper. We analyze the user-provided configurations with the source code, system source code jointly to derive a series of these rules, and with this assistance of these rules, users can easily troubleshoot these misconfigurations. And to make sure that our detected issue is not a one-off case, we conduct a survey on 48 user-reported issues on Stack Overflow and Serverfault. And here are our major findings. A number of silent misconfigurations are actually caused by the interaction between configurations, and our previous model example is in such a case. And also, many silent configurations are actually caused by syntax errors. This gives us a hint, which is we can actually implement a checker, and then before users plug in their configuration to the system, we can actually invoke the checker to proactively prevent the syntax error in the configuration. And the third thing is that a large number of silent misconfiguration actually happens without any system logs or messages. And none of our observed messages were useful to users, making troubleshooting prohibitively difficult for them. And from our survey, we also identified 5 different types of silent misconfigurations. The first two are syntax related, and the rest of three are semantics related. If you would like to know the detail, please refer to our paper. Here, we demonstrate our system overview of our ConfigX. There exist two major parts in our system: Translator and Analyzer. So the goal of Translator is to detect the syntax-related misconfigurations and also generates the IHA for our future use, for our future phase in this tool. And the Analyzer, this part, is to detect semantics-related misconfigurations and also use the program analysis to derive the rules of configurations. Let me dive into this one by one. First, Translator. So the Translator takes the user's configurations and system defaults and outputs a uniform intermediate representation consists of tuples of the form GI-CI-VI or a special closure statement like close GI here. So it is worth noticing that our translator takes different grammar of different configuration systems like Apache, MySQL, PostgreSQL, but it will be parsed into one uniform intermediate representation for us in ConfigX. Let me show you a concrete example for you to better understanding this translator. So, for example, the left part is the user's configuration C, and the right part is our parse IR. So from the example, so these 3 lines of red code, user specified in the configuration C, will be parsed into those two tuples in our parse IR. And actually, in this case, we have detected this line, config1 value 1 as a silent misconfiguration, and because this guard holding on this configuration 1 is module 0 equal to loaded. However, this module was never loaded before, making this guard hold on this configuration not valid. So we have detected a missing module here. In addition to that, we also detect another silent misconfiguration here, which we call unmatched guard. So from this example, what we can see, there are 2 different modules introduced in this code snippet, but only one of them has close. So in this case, basically, this case is a U-formed configuration. So in this case, we have detected that this guard 3 is an unmatched guard. And we also reported these cases to users as well. And after this translator part, then we move on to the analyzer part. So our analyzer takes the system source code. The first step is to translate this into LLVM, and we run our static analysis on the fly of LLVM. The reason we choose to do this design is because we want to make our tool as generalizable as possible. So if any system can be translated to LLVM, and our tool could possibly handle this. So the first part of our specification analyzer is configuration tainting. So the motivation, the goal of this part is to understand which part of the code snippet are related or controlled by the configuration. For example, take this order as an example. So we first identify this API in the source code, which is related to how configuration is passed to the system, for example here, and then we use our customized data flow analysis to track the usage of this configuration parameter all the way down to here, to the function here. And basically we track the usage of configuration, and then finally we will recognize, okay, these part of the basic blocks are enabled if the order was set to allow and deny here. And we do this for every configuration parameters in the system. So after this part, and then we will mark some pieces of the source code snippet is related by the configuration directly. And with this tainted source code, here comes our rule deriving part. So the right picture is a simplified version of LVM control flow graph. So from taking this as an input, our goal is to learn the specification of configuration directly via static analysis. So for example here, if user want to specify a configuration C like this, C1 equal to V1, C2 equal to V2, C3 equal to V3, and then in this previous configuration tainting or mapping part, this C1 will be mapped to this register 1, and then we will realize, okay, this block is enabled by the setting of configuration 1 to V1, and then we will color this block we represent this block with the same color as this C1 equal to V1, and then we do the same thing for configuration 2 and configuration 3. And then from this example, what we can learn is that So there is a silent misconfiguration here. So C1 equal to V1 is a silent misconfiguration. The reason why it is because the setting of the C2 equal to V2 will enable those two basic blocks and will set the value of inner variable x to 1 instead of 0. Although you will specify the C1 equal to V1, however, this value will finally be overwritten by the setting of C2 equal to V2. In this way, we have detected these rules. Override if user specifies C2 equal to V2, and then the setting C1 equal to V1 will be overwritten, and this will become a silent misconfiguration. So note that this is just a very simple basic example. If you want to know how our rule deriving works, please refer to our paper. And because our rule deriving is working on the file of over approximation of LLVM, it is possible that we derive a false positive in this rule deriving stage. And herein, we introduce reachability analysis to systematically prune out these false positives. So for example, take this picture as an example. We will compute the reachability condition with this register 4 and register 5 respectively, and then we will plug in these conditions to SMT solver Z3. So if our SMT solver Z3 tells us that, okay, it is unsatisfiable, which means that we cannot reach these two registers at the same time, and if there is a rule which involves both registers, and then this is guaranteed to be a false positive rule. So note that our reachability analysis is sound by using this method, and we have detected 34 these cases in our evaluation. Here in our evaluation, we answered two basic questions. The first one is that how effective is our tool in deriving rules. The second one is how many errors have been detected in real world. So this is the breakdown of our rules detected by ConfigX across three systems: Apache, vsftpd, and PostgreSQL. So the reason we choose these three systems because they are widely used open source systems, and we manually confirm the correctness of all the detected rules. And we use our detected rules and we run our tool ConfigX on these 5 datasets. 3 of them are for Apache, and 1 for vsftpd, and 1 for PostgreSQL. And we have detected more than 2,200 silent misconfigurations. And our detected advanced ordering errors has been recognized by an Apache expert saying that this is actually the #1 cause of HTTP 403 error. So it's very interesting that we can learn a lesson from our detected issues. For example, here, users specify the idle session timeout to 600 here, which means that this block is the intended block to be enabled here, right? But however, this block will never execute it in the code because the data connection timeout was preset to 300 by the system by default. So which means that unless users explicitly specify the value for this to less than or equal to 0, otherwise, any setting to the idle session timeout will automatically becomes silent misconfigurations. And from this example, we actually pinpoint the system design deficiency because if user ever want to specify this idle session timeout, the system should pops out error message saying that, okay, you should also change the data connection timeout. So this is an interesting lesson we learned from our detect issues. And because our tool is intended to detect the real-world misconfigurations, so we collected the cases from the online forum, and we ran our tool ConfigX on these cases. And we received 19 of the reports, and 16 of them, users actually confirmed the silent misconfigurations are true positives, and immediately used our report to fix it. The rest of this, the projects were abandoned. We didn't use our lab mate to do this user study, and we actually contact and interacted with the configuration owner in our user study to confirm the validity of our detect issues. Here it comes to our conclusions. In this work, we identify a new class of misconfigurations named silent misconfigurations. We develop our tool to automatically derive rules for these configurations, and we detect more than 2,200 silent misconfigurations in 3 systems. And our user study confirmed the validity of our detect issues, and we are really happy to see users quickly fix these issues with the help of our tool. Thank you.